Hey, welcome back to Fat Mama Physics. In this video, we are going to go over another conservation of energy problem. So let's get started. A pinball machine loads a pinball 5 grams and uses a spring with a spring constant of 10.2 Newton per meter, that's K there, that's mass in grams, while drawing the spring back 4 centimeters, that's probably some displacement. Of course, your pinball playing fields are not flat. When it reaches the end of the field, so probably here, the pinball hits the back wall with 1.2 meters per second. So speed here is 1.2. How much mechanical energy was lost due to friction? Okay, so we have some energy loss. So let's think about this to begin with. So I'm going to call this the initial point. I'm going to call this here hitting the back wall as the final point. Seems like those are the things we care about. This at the initial point here, we have a lot of stored potential energy in the form of elastic potential energy. So I'm going to write that as EPS for spring, not ESP. At the very back wall here, we have a few forms of energy. First of all, the ball is moving, so it does have kinetic energy. I can put that final. And since it went up 5 centimeters, it's not a lot, but it does have potential energy. And last but not least, at this point, we know some amount of energy was lost due to friction. So I'm going to write that as energy out of our system, okay? So if we have to put this all in the equation, it looks like the initial point, which is the elastic potential energy, is equal to all the forms of energy that I have here at the final point. Energy out plus kinetic energy and final potential energy. It looks like at this point we want to find out how much energy was lost. So this E out term right there. We can then put in all of the equations for the potential and the kinetic energies based on our data booklet. We know that the potential energy due to a spring is 1/2 kx squared. Okay, we know that kinetic energy is 1/2 mv squared, and final for final speed, and potential energy is mgh and final, mgh final. We don't have any potential energy, gravitational potential energy to start with. We're going to assume the ground here is 0. The ball, I believe, starts off from rest, so there's no kinetic energy to start off either. So then I believe we can put everything in our equation with a few things here. This mass is 5 grams, which converting to kilograms, dividing by 1,000, we get 0.005 kilograms. That's 3 decimal places. So putting all this into our equation, noticing that we cannot cancel mass because not every term has the mass. The spring constant is 10.2. It is being stretched 4 centimeters, which then converting to meters is 0.04 meters by dividing by 100. The mass is 0.005 kilograms. Final speed is 1.2 meters per second, 9.1 for acceleration due to gravity. And final height is 5 centimeters. And again, dividing by 100 to get meters, that gives us 0.05 meters. I'm going to do something which I don't normally do, which is calculating each piece out. So potential energy, for the spring, I get 0.00816. And the kinetic energy I get is 0.036. And then lastly, the final potential energy I get is 0.0024525. So now let's solve for the energy out by moving these guys to the other side of the equation by subtracting them. Which then my energy out gives me... Oh, I'm now missing another 0 here. My apologies. I get 0.0021075. This is why I like putting all my numbers in the end. Rounding to 2 sig figs, we get 0.0021 joules of lost energy. Doesn't sound like a lot of lost energy, but we don't have a lot of energy to start with anyways. So here we have, then B, what is the friction force? Okay, this amount of energy lost, if it's due to friction, That means the friction force was doing work on our system by taking away that energy. And we know that the work done on a system is work is equal to our force times our displacement, S. We need to find the force. We have the work done, which is this amount of energy that's being lost to our system. Remember, change in energy is equivalent to some work that your system does or something doing work to your system. You can also think of it as your system doing work on the ground, which therefore it will lose that energy due to thermal. As for the displacement, it is this one here. It's the ramp that's going up to the top of the cliff, top of the ramp, not 5 centimeters, not 20 centimeters, but assuming this is a right triangle, this is the hypotenuse of that triangle. So we need to find the hypotenuse first. So here I just wrote the sides in meters, and we know to find the hypotenuse, it is a squared plus b squared gives us c squared. And in order to calculate for the hypotenuse, we need to take the square root of both sides, giving us c is equal to square root of a squared plus b squared, which is just 0.05 squared plus 2.0 squared, all square rooted. And I get 0.2061, which I'm going to have to save it for later. So we have the work being done, we have the displacement, we can then solve for force by dividing both sides by our displacement. And we can just double check here, the work, the force and the displacement are along the same direction, or here we have the friction force, or rolling friction in this case, would be applied parallel to the ground, but going opposite to the direction of motion. That's the force of friction, while the object is moving forward. So since they're in one line and short, the force of friction opposes the displacement, making it as if you're taking energy out of your system. We don't have to worry about the negative sign because we know this is energy being lost as calculated in our previous question. So then we don't need to worry about a cosine factor, a cosine theta. So we can just go ahead and solve for the force by dividing the energy by the displacement. And don't forget to save all our significant digits. We get the work being 0.0102. And rounding this off to 2 sig figs, we get 0.010 newtons. Whew, okay, long question. So we got one more, C. Okay, C is asking us for the coefficient of rolling friction. So I'm just going to write mu for now. And we know that mu comes from the force of friction being mu times the normal force. And to find a normal force, we have to draw a free body diagram on this ball. As the ball is rolling up the hill, there is gravity acting on it. We just talked about how friction is opposing that motion. And last but not least, we have the normal force in a direction that is perpendicular to our ramp. We don't have the angle of this incline, but we know this side is 5 centimeters and the bottom is 20 centimeters. We need to resolve the fx into its components, assuming our x-axis is along the parallel to the incline, and the perpendicular axis y gives us for force due to gravity, in which the vertical component of that relative to the y-axis is going to be equal to our normal force, because there are no other forces along the y-axis, and our object is not going to travel or accelerate along that axis either. So our up forces equals our down forces. And from inclines, we learned before, if you don't remember, refer to a previous video, we know that this angle here is theta. So then to find FGY, this is just FG times the cosine of theta, because this side is adjacent. And FG is just mg, so we can further substitute that. You might be thinking, oh, I don't have the angle. How do I get this angle here? Yep, it is the angle that we need to find. Is the angle from this incline here. It's the same angle based off of geometry. So to find this angle, we have 5 centimeters and 20 centimeters. So if it's adjacent and opposite to this degree, this angle here, we can use tangent. So our inverse tangent will be 5 centimeters divided by 20 centimeters. And that gives us 14-ish degrees. So then we can rewrite this over here. This is mg cosine of 14, which I'm actually going to use a non-rounded value, as fn. So let's put this back all the way over here. And now we can solve for mu by dividing both sides by this mg cosine 14. Again, mu is equal to force of friction divided by mg cosine 14. Putting in our force of friction, mass, gravity, and cosine values, we get 0.21. Okay, so here we have the 3 parts of this very long example. If you fully understand this problem, you can replicate it, you could do it yourself, or similar challenging or difficult problems like these. Good for you. You are ready to do example 4. Okay, so let's go over this question, and I'm going to actually get you to try this question out yourself. We have a 100-kilogram skater, starts at the top of the incline, begins to make her way down the incline without using her legs to pump up the speed. So I'm assuming she starts off at rest and just rolls down. The incline has these following dimensions. Assume no air resistance, but there is friction. If the skater cleared the bottom of the incline with 10 meters per second, how much energy was lost? What is the force of friction? And what's the coefficient of friction between the skater and the incline? Probably rolling friction. Okay, so this is a good time to pause the video and for you to try out this problem. Okay, so I will do the solutions on Fast Play. Okay, at the very top of the incline, we have full potential energy, no kinetic energy. All that potential energy gets converted to kinetic energy at the bottom of the incline. So no potential energy left, but then some energy is lost due to friction. So if we have initial energy equals final energy, that is potential energy equal to kinetic final energy and the energy leaving our system. So solving for the energy out, we get the following, and then to put in potential and kinetic energy equations, we get the following there as well. Substituting mass as 100 kilograms, the height is 10 meters above the ground, as well as the speed is 10 meters per second at the very end. Putting all those values into our calculator to solve for the energy out, we get 4,810 joules. Now we're going to do question B, which is finding the friction force acting on the skater. And we know that this energy loss is the work that is done by friction that's being taken away from our system, and which it will heat up the surroundings, including the wheels and the incline there. So we know work is force times displacement. We just need to check if the force and displacement are along the same direction. And based on our free body diagram, they are opposite in direction, but since cosine 180 is just -1, and the minus sign is just going to give us the negative direction for our friction, we can just go ahead with that, in which the work done is just the energy loss, 4,810 joules. We need to solve for the displacement, which is the hypotenuse of our triangle, in which we're going to take 10 meters squared plus 20 meters squared, all of that square rooted, 22.36 meters. Dividing them both, we're going to get the friction force, which is going to be 215 newtons, rounding out to 3 sig figs. That's what we get there. And that's actually going to be up the ramp, since the ball is rolling down the ramp, since she's going down the ramp. And that just reminds me, I got to write down the incline for the previous question there. Okay, so now we're going to solve for mu, for a coefficient of friction. Now we know the friction force, we need to know Fn. Drawing our free body diagram and solving for Fn, we have Fn is equal to Fgy, because there's no acceleration along the y-axis degrees there. So to find FGY, that's just FG cosine theta or mg cosine theta. We can substitute that back into that equation that we had before. So that's a mu times mg cosine theta. Now we need theta value, and to find a theta value, we need to use our triangle here. And we know the bottom is 20 meters, the side is 10 meters. We can use tangent to solve for that. So inverse tan of 10 divided by 20 is going to give us an angle of 26.56 degrees, which then we can put into cosine theta over there in our equation. So then we can rewrite that out. And then what we're going to do is we're going to solve for mu, which means we need to divide mg cosine 26 on both sides to isolate for mu. And putting in all our values, which include force of friction is 215 newtons from the previous question, the mass, gravity, cosine 26 degrees, and putting that all in our calculator, we are going to get a mu value of 0. I believe is 245, 3 sig figs, and that's what we get. Okay, and here we have the final solution to this example. Very similar to the last problem, except the skater is going down the ramp instead of she going up the ramp. But everything is pretty much the same, except I forgot something, and this is my fault. Whenever we are talking about a vector, such as friction force, we need to specify the directions, which in this case, this friction force is going up the ramp because skater is going down the ramp. Friction force opposes the direction. And that's what I forgot to tell you in the last problem. So instead here, it will be 0.01 Newton going down the incline because the ball is going up the incline, which the friction force opposes that. So if you forgot to put in the direction, that's because it's my fault. But in future problems, be mindful. You need directions whenever you are describing a force, okay? Otherwise, good job for getting through this video. You did fantastic. Conservation energy is a big topic, and it kind of puts everything together in this unit. So job well done. Keep at it. Good luck with your problems. Thank you for watching this video. Fat Mama Physics signing out.